Hello everyone, so my name is Arkady, and so today I'm going to talk about the architecture of Kotlin Multiplatform projects, and in particular what can we do for better scalability and maintainability. But before that, I required to give some disclaimer. So even though I work for Google, this is unrelated to my employment at Google nor my role there. So all opinions are my own. So I've been looking around the community, open source projects for different architectures. They are mostly samples. Everyone likes to write samples. There are quite a few production open source projects, or at least on GitHub. But what works well in sample projects might not be a good fit for a production project at scale. So anyway, there seems to be a noticeable pattern that many projects use. So they tend to create one single shared Gradle module. Usually it's called shared. And there are a number of view models in that shared module. Typically one view model per each screen. And then there are app modules for each platform. Let's say one for Android, one for iOS, and so on. And each app module contains the platform-specific UI and navigation. And this works pretty well in a sample project, but shared and platform-specific things are separated. It's easy to browse and through the folders and etc. But there are also some problems with this approach. So let's consider some use cases. What if we need to add a new screen, for instance? We have to not only change the shared module, but also update both app modules. If we need to remove a screen, again, also touch the app modules. Need to change communication between screens? Yes, again, we have to update app modules. And if we want to change navigation logic, same, we should touch shared module and app modules as well. So the whole project is affected. Another concern is that all modules grow linearly. Almost every time we add new code to a shared module, we have to add counterparts to the app modules. Unfortunately, this affects the maintainability of the project. Just imagine a module like 100 or 1,000 view models, their dependencies, and all that stuff. Another side effect is the increase of chances of merge conflicts if your team, for example, has like 20, 30, 50 developers. And it's also not good for build times. We can partially improve the situation by splitting the shared module by a number of feature modules, let's say, but still having monolith application modules is not good at scale. How can we do better? Let's consider an example, the Twitter app, or now it's X, that most of us should have handy on our devices. As a disclaimer, again, I don't work for Twitter either, so it's just a social network, and its mobile application looks a good example for a complex project. So the first screen the user sees is the landing screen. This is the step where the user decides either to log in, or if there is an existing account, or to create a new account. If the user selects the option to log in, they go through multiple screens where they can enter some details like email and password. If they choose to sign up instead, then Flow contains screens to personalize things like ads and some other things. And once the sign-in or sign-up flow is finished, the user is taken to the home screen. This is the default screen which the user sees when they open the app, and so on. From the home screen, the user can go to different places, like profile settings, or when they click on a tweet, the tweet screen opens. And the home screen is not just a single screen. The user can use the bottom bar to switch between other screens like search or spaces. I think they removed the spaces tab now, but who knows. Of course, there are more screens in the app, and there must be a lot of code. So how can we organize all that? How can we allow different teams to work productively on the same code base? How can we make sure that the code is testable and maintainable? I'm going to present an interesting approach. I call it thinking in scopes. Let's again use the Twitter app as an example, and let's decompose the app by a number of scopes. This is just an example. Nothing related to the real app, I think so. So the topmost scope is the root scope. This is the scope that is created at the very beginning of the app's lifecycle. It holds everything that works in the app. All the logic, repositories, data sources, everything is inside root scope. It's not the module, it's not a class, it's a like abstract scope, let's say, for now. Everything that should exist only while the user is not signed in can belong to, let's call it, signed out scope. This scope can contain additional subscopes, sign in and sign up. The sign in scope holds the login flow, and the sign up scope holds the registration flow. The landing screen can live in its own scope, so the parent signed out scope, the green one, controls the 3 children and switches between them when necessary. The sign in scope contains screen of the login flow. Its responsibility is to switch between child screen or child scopes. And the same story with sign up scope. It contains screen for the registrations flow and navigates between them. And once the user is signed in, the root scope can destroy the sign out scope, the green one, and create another one, the signed in scope, orange. This scope exists while the user is signed in. On logout, the root scope can switch back to the sign out scope. Here we have the main tab scope and other child screens like profile settings or tweet. The signed in scope, orange, can switch between full screen scopes. For instance, when the user clicks on a tweet, the signed in scope can push tweet into the stack. And lastly, the main tab scope contains 3 tabs, home, search, and spaces. Every time the user clicks on a tab in the bottom bar, the main tab scope can just replace the current screen with another one. So the structure that I have just described is actually a tree structure. Each parent node is only aware of its immediate children, and each such node has a very limited responsibility, either to hold and manage the logic of a scope or to switch between child scopes. And yes, the tree structure is scalable. For instance, if you want to add a new module, like a new screen, for example, we just add a new module and attach to a parent. In most of the cases, we have only to touch one specific parent scope, and our new module is there. If you want to remove a screen, it's also easy. Just delete the child module and update the parent, and it's gone. A module may become bloated and difficult to maintain. In this case, it can be decomposed by a number of smaller submodules. Each with more limited responsibility, the parent module would simply manage the children. Same if you want to change communication between child scopes, just update the parent module. Change navigation logic, update the parent. In a tree structure, each module has limited and meaningful dependencies, so there are no God modules. Obviously, this reduces chances of merge conflicts in big teams, and it's good for build speed, as more code can be compiled in parallel. But how can we actually implement that? Let's think about requirements. Every parent node should be able to manage scope of its immediate children. That means that child scopes should never be longer than the parent. And it should be possible to easily switch children in a parent, which means we need navigation. And nodes should be lifecycle aware, so we can scope tasks inside a node, for instance, cancel a task on destroy or refresh data on resume. And last but not least, it should be possible to save state in a node. This is useful for handling configuration changes and process deaths, not only Android. It is also possible to preserve the state on all Apple targets and on the JVM targets. There is a library example exactly for this purpose. It's called Decompose. It helps to break up the code into meaningful lifecycle-aware components organized as trees. Each component has its own scope, and there are tools for switching subtrees, or in other words, navigation. Let me describe a few most important features. First of all, Decompose draws clear boundaries between UI and non-UI code. This gives the ability to plug almost any kind of user interface, like Jetpack Compose, Swift UI, or React. And also it makes components easy to test with just normal unit or integration test and without instrumentation in most of the cases, which is fast and reliable. It also enables classic dependency injection and inversion of control. This is very useful in large projects when a component should be reused in different places. You just supply dependencies via constructor. The navigation logic can be shared, and components are lifecycle aware. This makes it possible to scope background task and handle lifecycle events. And of course, it is multi-platform. The core of the library supports Android, all Apple targets, JVM, and JavaScript. There are also some additional features like convenient state preservation and instance retaining, also known as view models on Android, and back button handling. There are also separate extension modules for Decompose and classic Android use. Here you can see some links to most interesting sample projects that showcase the Decompose library from different perspectives. The first one is a multi-purpose sample app. It showcases different kinds of navigation. It's right in the main Decompose repository. The second one is a to-do application. It's a simple list details application with multiple feature modules. I think it also has SQL Delight library inside it and some other libraries. So previously it was in the JetBrains Compose Multiplatform repository, but they decided to remove all third-party things from the official repository. So now it's extracted by a user of my library to a separate repository. And the third one is a Confetti application by John O'Reilly, which is a conferencing app. Some of you maybe know this one. So let's start with a brief explanation of the most important entity of the library. What is component? So first of all, it's just a normal class. So any class can be a component. Components can encapsulate some logic, just like well-known view models. And they can also encapsulate and manage other child components. And every component has its own lifecycle, as already said, and automatically controlled by Decompose. The user interface is attached externally. Components never depend on the UI, but the UI depends on components. And now let's walk through some simple examples. As I mentioned earlier, any class can be a component, even an empty one. So Decompose doesn't require classes to extend any base or abstract class or to implement any interface. But most likely you will find it useful to extract an interface. So some use cases could be to inject test implementations when testing parent components. So you can basically fake your child components and fake the events, and the parent component can react accordingly, and you can test that behavior. Or you can provide separate implementations for previews in Jetpack Compose or SwiftUI. But this is optional. So if you need an access to lifecycle or back button handler, or if you need to preserve some state, or if you need navigation, then component context should be supplied by constructor. Component context is a second entity of the library. Each component has its own component context, and Decompose always provides dedicated context for every component. It's up to you if you want to inject it or not. Component context is just a simple interface with a few properties, and it's not related to Android context in any way. It provides access to the lifecycle by corresponding properties. There are also tools for state preservation, instance retaining, and back button handling. And all this together makes it possible to integrate and scope child components with persistent navigation. As mentioned earlier, component context is a simple interface, so we can use Kotlin delegation to bring component context into this scope. The lifecycle is very similar to Android. I think most of you should be familiar with this one. Basically the same flow. It starts with initialized, then it goes to created state, then started, resume it, and back to started, created, and at the end destroy it. And lifecycle can be accessed by the corresponding property. It's possible to subscribe to lifecycle events, like on start, on resume, on stop, on destroy, and so on. And it makes it possible to scope background tasks. For instance, we can define a coroutine scope and cancel it on destroy, or we can dispose any disposables if you use any RX library, for example. And also, it can be accessed by the corresponding property. It's possible to subscribe to lifecycle events, like on start, on resume, on stop, on destroy, and so on. And it makes it possible to scope background tasks. For instance, we can define a coroutine scope and cancel it on destroy, or we can dispose any disposables if you use any RX library, for example. And now about child components. So creating and managing children with Decompose is easy and safe, and it can be done in different ways. The simplest way is to just create your child component directly in a parent. These so-called permanent components. So this live as long as the parent. As I mentioned earlier, Decompose provides child context for you. So in this case, you can use this child context extension function, which gives you basically a child component context, which is already attached to the parent, so you can just inject it. And we can also manually control the life cycle of this child if you want to start and resume it when you like. But managing child components manually may be tricky, especially when you have lots of them and you need navigation. Then for this case, there is a child stack navigation module. So it's important to understand some key concepts of stack navigation. For example, here is the first one. Each component in the stack has a configuration class. So you can think of it as a serializable holder of arguments. You have to define a configuration class for every child in the stack. To initialize the stack, it is required to supply a child factory function. The function accepts two arguments, a child configuration and a context. And it returns a new instance of the corresponding component. So this is the place where you call the child constructors, and here you can safely supply your dependencies and arguments. Configurations are unique keys. They must properly implement equals and hashcode methods, or just be data classes or data objects since Kotlin 1.9.0. And configurations are persistent, so Decompose is able to automatically save and restore the stack when it's needed. And so every configuration class must implement the parcelable interface, which is provided by Decompose as well for you in common code. The library also provides personalized annotations, so make sure you have Kotlin personalized Gradle plugin applied if you're targeting Android, and it also works on Apple targets. And the last concept specifies how the navigation is performed. The navigation is just a function from the old configuration stack to a new one. So the basic navigate method accepts the transformer function that changes the stack. And Decompose compares the new stack with the old one and automatically switches components for you. So here's an example. We can define a couple of child components. They can accept any kind of dependencies, including callbacks. In this case, the main component accepts its own context, and it also accepts a main coroutine context and an on-item selected callback, which is invoked when an item is clicked. Details component also accepts the main coroutine context and an identifier of the item to be displayed. As you can see, we benefit from strict type safety here. It's not possible to mess with types. The project will not compile otherwise. In the root component interface, we can specify all possible children as a sealed class or interface. And later this will allow us to exhaustively handle all children and also avoid any type casting. In the root component, we have to define a configuration class for every child component. In this case, we need two classes, main and details, and we can also define persistent arguments for example, item ID. Again, we have full compile time safety here. And now we can add a factory method for children. We create them by calling constructors and supplying all arguments, and as usual, strict compile time safety. And the same for details component. You can see that persistent arguments are taken from the child configuration, and non-persistent arguments can be created on demand or just taken from the parent constructor. And basically, at the end, you add the main child function that exhaustively switches configuration classes and creates children when needed. And yes, and now we need to initialize our navigation. So the first thing, we create a navigation class, which is like a simple relay where you can supply navigation events. So when you need to navigate, you call navigation.push, navigation.pop, and so on. And lastly, you use child stack extension function and supply all arguments there. So the source is navigation. So child stack will subscribe to that relay and will listen for your events. And you can also supply the initial configuration, which is, in this case, it's main. You can also supply a stack of configurations, for example, for deep linking. And you can also supply handle back button arguments, so it will pop components when you press the hardware back button. And lastly, you supply child factory function reference, so you can create components for you. As I said, you can use navigation to push a child. For example, in this case, when an item is clicked, we just push details there, supplying arguments. And as I said, the navigate is just a simple transformer function, so you can do any kind of navigation. You can like reverse the stack if you want, or you can shuffle it. And child stack is not only the only navigation model offered by Decompose. So there is child stack, as I described it, which is a stack of components, and the top one is always resumed, and the components in the back stack are created and stopped. And another navigation model is child slot, which is like either one component is displayed or nothing, which is useful for things like dialogues or bottom sheets and so on. The third one is child pages, which is useful for paging navigation. You have a number of components in a pager, like user can slide them back and forward and backward. You can attach them to compose horizontal pager, for example. And if nothing works for you, there is always generic navigation as a fallback option. You can use this to define your own full-featured navigation API for your needs, which allows almost like any kind of navigation. You can switch components as you like, manage the lifecycle events, and it's declarative as well. But what about user interface? So as I mentioned earlier, the user interface is plugged externally. Components do not depend on the user interface, but the user interface depends on components. And here is an example of how can we display the child stack. So we should expose the child stack state from the component and make it observable. And one of the ways, just one of the ways, is to use value. It's a Swift-friendly way of exposing stateful observables provided by the library, but you can use coroutines flow or Rx instead of value if you like. After that, we should just override the property in the root implementation and return the child stack. And now we can display the stack. For instance, Decompose provides the children function for Jetpack Compose that automatically displays only the active component. And this is a place where we exhaustively switch the children. And it's also possible to specify different kinds of animations. There are some animations available out of the box, or you can define your own. For example, this is the sample of crossfade animation. This is a slide animation that basically slide horizontally. You can also combine animations with the plus operator, and basically, in this case, it's fade plus scale. And it's also possible to provide different animations for different child components. In this case, the main animates fade plus scale, and the details fade plus slide. And it also supports predictive back gesture since recently, and both Android and iOS. On Android, it works basically, obviously from starting with upside-down cake version, where it was introduced, but on all other targets, including Apple, it works on all possible versions. And due to the fact that the navigation state is observable, you can leverage the usual API of your favorite UI framework and render the stack as you wish. In this case, it's multi-platform compose. And as I mentioned earlier, we can plug any kind of UI, like Swift UI for iOS, Compose for desktop, or React for web. We can do simple or multi-pane layouts, and even dynamic layouts. And I think that's all. So here's a link to the repository where you can also find the documentation and samples, and my Twitter handle if you want to subscribe. And later you could grab some nice stickers from me, so please pop by.